あ、はい。はい、ありがとうございます。ちょっと待って、ちょっと待って。
So pay attention. Now we are on the stream.
そうです。で、もう一個のオープンルームにみんなが入るんですけど。YouTube じゃなくて。
So during the challenge, otherwise we can turn off the camera and give to the team leaders or team members.
Zullen we het wat minder lawaai gaan maken, denk ik. Dat heb ik er alles op.
Good morning, good afternoon, maybe good evening for everyone. We will start at maybe in just 1 minute. We will start the technical challenge here.
Good morning, good afternoon, or maybe good evening. Now it's time for middle-sized league to have our technical challenge here. First, I will say thank you very much to come here to take our challenge here. And for this challenge, we will have 7 teams to take technical challenge. The first one, let's invite Team Funkhongs and Team VDL Robot Sports from the Netherlands to give the first challenge. Team Funkhongs and VDL, can you hear me?
Yes, we can.
Now I stop share my screen and it's up to you.
Okay. Okay. So.
Recording in progress.
Okay. Hello. Good morning. Good afternoon. Good evening. Today, Jan Feitsma and I from ASML Falcons and Robot Sports will present the mixed team protocol, a protocol that allows robots of independent developers to play together in one RoboCup MSL team. And during this presentation of the technical challenge, we will demonstrate the technical complexity of the mixed team, as well as the results that we have achieved. So the original mission of RoboCup was to field a team of robots capable of winning against the human soccer team, the world champions by 2050. RoboCup is now an international scientific initiative with as goal to advance the state of art of intelligent robots. But what does it mean to move towards the original mission? One thing is that teams need to grow in size over time to 11 field players. However, this gives rise to some challenges. How to fund 11 robots? Some teams, if not all, struggle to fund already 5 robots. So how to fund 11? Another one is player diversity. Nowadays, most teams choose to develop identical field players from hardware perspective. It saves complexity and cost, but it does withhold diversity and specialization of robots like you see in human soccer, which limits innovation options. Mixed team offers a generalized method for robots to interact within one team. This allows robots from multiple developers to be brought together in one team. Moreover, it allows independent development teams across the globe to work on specialized robots that can play as one team on a match or tournament. Just like how players from club teams play together today in national teams. The advantage to developers is that participation in RoboCup MSL is already possible with just one robot. This lowers the budget demands significantly and also lowers the threshold for participation in RoboCup MSL. Developers can also have a more dedicated focus on special player capabilities like defending, attacking, free kicking, or even heading. Another possibility that mixed team opens up is the availability to play together with humans in one team. What we present here today is a summary of the practical experience that Falcons and RoboSports have gained with mixed team by implementation and demonstration over the past half year. Let's start with a video that shows our collaboration in developments and our achievements. So, in this video, you see the robots of PDL, RoboSports and Falcons play together in a number of set play situations.
In the last MSL workshop in November last year, we talked about the mixed team, which has as aim that robots from multiple vendors can play together in one team. Today, we are gathered here with the Falcons and PDL RoboSports to have their robots play together in one team. To do so, we have prepared over the last months mixed team protocol layer, which solves the problem of data communication between the robots and also the interaction with the RevBox. And yeah, today is our test day to see how far we came and to see what we have actually achieved.
In order to let our robots play together, of both our teams, they need to, of course, decide on the role allocation and not change their minds too often in a way that they would conflict. So we need one of the robots to choose to become the goalie, and typically a goalie knows itself that it has the capability to become a goalie because it has the hardware to do so. So those typically in the protocol will then claim the role of the goalkeeper. And for the rest, it's more dynamic. Mixed team protocol takes the responsibility of distributing the roles, but robots can still, similar to the goalie, claim set a preference for a role. And to be added later if we are also going to take the current world state into account, such that the robot closest to the ball actually becomes the attacker main. But these things are all still in progress.
Okay, now let's hand over to Jan for a more detailed description of the mixed team protocol.
Hi, I'm Jan from the Falcons, and let's deep dive what we did here on the mixed team protocol layer. Summarizing, of course, it's making the step from the traditional adversary setup, where we oppose each other, towards playing together, mixing our team's robots. Some general notes. This is not new. This is invented in 2014, where we did the first package definition. However, the changes we did in this demonstration is to make it more scalable towards the future 11 players and address some gaps. One gap is the role allocation, which was not there in the original protocol, and the other one was the refbox signal handling. Underwater, we now choose to use RTDB and its communication facilities, because you can consider them nowadays MSL standard technology. Yeah, and it also makes it easy to handle refbox listening. The library is now more than just a packet definition. We provide a header and a library implementation, which might be accepted as the MSL standard, depending on your feedback, and maybe in a common discussion in a coming workshop. So how did we integrate it in our teams? Yeah, in the team play and world model components of our VDL and Falcons software stacks, we just get and set the data via the interface and make the mixed team protocol calculation do its the library do its calculation. Yeah, so let's zoom in on the role allocation. So given a set of allowed roles, how to decide which robot takes which role and prevent conflicts. Next, yeah, we made some choices to select a leader or elect a leader if you want, and the leader calculates the roles for the entire mixed team, taking preferences into account, which can optionally be set by the robot. And the use case, which we already also mentioned in the video, is of course the goalkeeper. Yeah, typically you have one goalkeeper, but it needs to become the goalkeeper. And if the goalkeeper is not there, then any of the other robots should take over. I think all of our software, all of our teams have similar logic. So in this case, the goalkeeper just claims the role of the goalkeeper. Alternatively, another example could be an attacker main, which happens to be close by the ball and takes the initiative of taking a set piece or a penalty. The algorithm of role assignment uses standard assignment and the Hungarian method. And we played a little bit with linear programming as an extension, a generalization, but it turns out a little bit more complex. So we went for the other alternative for now. Another challenge is world model. For now, also in the original protocol, an example is how to filter obstacles from teammates. This is left for the client. So the data on the interface is interpreted as raw data. So it's up to each team's world model implementation to make sense of it. And this was the original design choice. However, given the experience and the discussions we've had so far, we are considering, should we maybe bring this responsibility into mixed team protocol, basically standardizing the world model. And a benefit could be that, we are preventing highly similar implementations, especially useful for new teams, which can take years to get the basics working in world model. But however, the more mature teams might argue that it's too limiting and not customizable. So for the future, we could maybe discuss how to go for a software architecture to satisfy both use cases. But this is for the coming workshop, I would propose. The final big challenge is how to include humans. So with the interface and the packet layer we have now, it's quite easy to spoof and to fake a robot in this mixed team protocol. You just have to send packets from anywhere on the network, laptop. And for a guy like me who is lazy and does not want to put the robots on the field all the time, it's useful. You just fake the goalkeeper, the second, the third robot, and you can play test with only an attacker main, for instance. And of course, this extends into inserting a human player. Because for the human player, you have to generate similar packets, but then, and you can do that with an external system, which sees humans and reports the coordinates. Or you can even, once the robot can do this, we are still working on that, more tomorrow in the scientific challenge from Falcons, from Andre. If the robot itself can detect humans, then it can also put these on the mixed team protocol network. With more challenges which will come up by that time, which is of course how to select the good, how to assign the correct human to the correct team. We probably need to do something with shirt coloring. Yesterday we had an integration session of integrating mixed team protocol and human detection. So we are going to also have a second video demonstrating how passes are being made between a robot and a human player. We put two robots on the field, we fake the goalkeeper, and we use a static camera mount with a very simple, genius wide-cam camera on top of it, and insert the data as a human mixed team protocol client, which runs, the software stack then runs on our base station laptop. We configure it to claim the attacker assist role, which is good for the demo. It will cause the robot to pass to the human. Connect to the camera, of course, and using our vision prototype YOLO system. And we only communicate human and ball coordinates for now. Now, this is a prototype. It's only running at 4 Hertz, but you will see in the video it's already good enough. And as far as precision of coordinates is going, with little calibration method, a little calibration effort, we also got quickly into the good enough domain, well below 0.5 meter accuracy. So the movie then.
Start.
You can see the human detection live here in the bottom. The robot will now used to do another pass after a bit of. Yeah. One more.
Stop. Start.
Oh, no. Not again. Next. Yeah. Now I will hand it back to Rob, who will explain a bit more about the RTDB and the RevOps layer.
Hi there. So, yeah, so a lot of robots in robot teams already use RTDB based communication to play with their teammates. The communication typically uses some fixed and hard-coded agreements between robots. For example, shirt numbers and network addresses are often hard-coded within one team of single vendor robots. In a regular robot team, you also see a proxy application, a so-called coach or sideline that receives RevVox signals like the free kick or start-stop signals, and broadcast these in a proprietary manner to the robots on the field. When forming a mixed team, these approaches can no longer be used. Shirt numbers are no longer unique to one robot, and RevVox signals need to be communicated in a unified way. Also, entering and leaving a mixed team, as well as switching between teams, needs to be facilitated and also be made easy, just like changing a shirt in human soccer. Therefore, shirt numbers, network addresses must be made independent of the communication protocol. On tournaments, cumbersome and error-prone match setup must be avoided. Instead, it should be straightforward for any robot to participate in a mixed team. On the practical side, maintainability of software needs to be addressed. Otherwise, the adoption rate remains low and the investment to participate with mixed team is too high. So this led to some extensions in RTDB. And one of these is the unique identification of robots in the world. Another one is that we want to be able to have more than one database, where the database denotes the data structure that is communicated, or in more simple language, the language that robots speak among each other. And thirdly, we would like to have more than one communication network in parallel, where a network denotes the group of clients, in this case robots, that speak one language to each other. These groups need to be flexible, as the robots need to be able to change teams. Not all clients join the same group, as they join different teams, but they do speak the same language, being the mixed team protocol. So this slide shows the network architecture for mixed team. It shows two mixed teams, each having 5 robots, 2 + 3, of 2 makes, and a RevVox for referee controls. At the bottom of the slide, you see the RTDB-based intra-team network for each team for the communication between members of a team. Between the team and the RevVox, there's an RTDB-based referee network for each team to receive RevVox events. Each of these network types has its own database structure, its own language, a mixed team database structure, and a RevVox database structure. When the referee triggers a new state, so let's say kickoff, then this event is forwarded to the robots via this network to the robots on the field. Next, the robots determine their role, as Jan explained, using the intra-team mixed team network and initiate appropriate action. The mixed team network is then also used to share data like actual position, detected ball, and detected obstacles. At this moment, we use a small client to translate from the RevVox API to the RTDB network. to the RTDB network database structure. Preferably, we would like to integrate this directly into the RefBox. We would appreciate if somebody involved with the RefBox would be able to contribute to this. So we can finally achieve this type of network. So for those who are a bit more involved in RTDB, this is a slide that shows in more detail the capability and extensions that we have made. This slide shows the separation of the database structure, the communication network at the bottom, and the process that takes care of the communication itself, the COM process. None of the clients in this picture has a priori awareness of the existence of any of the other clients or their identity. This is all discovered at runtime. So in this example, we see that the COM process on device 3 publishes the data from robot 3, and then exposes this on this network where it's received by this COM process or this client on this device, where the client on device 1 can actually read the data. In this way, you create local copies of the remote databases. And what we've done here is to prevent the tight coupling between database structure and the network, and to drop the restrictions on client identification. So, and then for the final slide, back to...
Time is up, so be quick.
Time is out, okay. Thank you.
Maybe some questions?
10 minutes for your questions. If you
Go ahead.
leaders and other members here have questions, please open your mic and say your question directly.
We are not hearing questions.
I am not participating in this as a Kambada member, but since I met an exec and Ehsan just remembered me by email that I can be here and ask questions, not vote, of course. But I just saw that there is a need for someone that has been involved in the RefBox to allow the integration of that module that you referred previously. What exactly, if you can describe it in a simple way, does that mean? Or what kind of software component you need in the RefBox so that this could be easily integrated and used by other teams?
Yeah. So what we would like to do here is that the functionality that we now have put in this small RefBox client, that functionality is then integrated into the sorry, that doesn't work. That functionality that's integrated then into the RefBox. And basically, what this client does is a translation between the current API, so the one that's published of the RefBox, and the API that we use within the mixed team, which is then based on RTDB. So basically, the functionality would be to put some RTDB capabilities, to publish capabilities into the mixed team, so it can directly publish this data, so we don't need this additional client anymore.
Okay, but is your idea to keep both in parallel, so that
Sure.
other teams, okay, so that other teams that would not have to use that RTDB-based model in particular, right?
Oh no, that was not the intention. It should just be another method for teams to receive the RefBox signals.
Okay.
Not to abandon the existing one.
Okay. Of course, I'm not promising anyone anything, but I think that that's doable. It's just a matter of time, of course. and looking into it. And I think that later on we can discuss some of those details and look into it and see what is required to integrate that in the red box.
Yeah, I'm already very, very glad with your response. So thank you for that.
Well, you're welcome.
No other questions? Then maybe give it back to Fai.
You still have 2 minutes for the first 2 teams. 2 minutes.
If no one has a question, I still have one, maybe a short one. I think that of course, I think this mixed team protocol can rather be very interesting in the future, because that's in the end, I think, the only way to actually think that we will be able in the future to play with a larger teams. And no one actually is probably investing in creating teams of 10 robots or so. So I think this is rather interesting. But my question is, I think the harder part on this is to create some sort of shared strategy model.
Next is Iris. So are you ready, Iris? If you are ready, please try to go to move the competition room.
Mute mic. Please go on.
Okay. Sorry, I don't know if you were listening to me or not, but
Yeah, we are.
okay. So
yeah, where are you?
I was just placing a single question with what's your global idea regarding the higher level of abstraction, so that 2 different teams that may have 2 completely models in terms of strategy and agent generation can actually work together.
Yeah, obviously that needs attention. But what you saw today in the movies is the robots each still applied their own behavior as we've developed ourselves in our own teams. So there is no that has not been changed yet. The only part that we addressed here now is the role allocation to make that work between the robots with different vendors. But anything about the strategy that they apply to these roles is still the strategy that they originally had. And apparently there's already some level that they can play together. So that's already very interesting, I think. But you're right. Yeah. We together need.
Next is Iris. Are you ready, Iris? Please go to the competition room.
A robot-dependent part, but actually a team-dependent part. So it means involving all the robots, right? So
exactly.
It's just not applying or giving a certain role to a certain robot normally. But okay, thank you for your answer.
Yeah, thank you for your questions.
Okay, thank you. So if you have finished your challenge, please leave the challenge room, competition room. Now I will invite the team from Iris.
Test, am I audible?
I can hear you. Could you please wait just a few minutes? It's not the, we still have 3 minutes to change the teams. I see you still have team members want to come into the competition room.
Okay. We still have 3 minutes to prepare.
Yeah, your challenge should be start at 35.
Oh, 35, okay.
I don't know which the clock, but what is the clock? But the minutes should be the 35.
Yeah, yeah. Okay, thank you.
I see lots of people want to come into the competition room, but the most important thing is please don't forget to change your name plus the team name.
Okay, I will tell them to change their name.
So it's almost time. Next team will be the Iris from Indonesia. Iris, I will stop share my screen and you can share your screen. And 10 minutes for presentation and 5 minutes for the, oh, sorry, I forgot to share the screen to show you page. Yeah. Okay, next team will be the team Iris. And now I will stop share my screen. It's up to you.
Okay. Greetings, everyone. We are from Iris. My name is Banin Fawzadin, and I'm a representative from Iris. And I would like to share a little bit about our team. We are from Indonesia, located in Surabaya City. I'm sorry, Failyu, can you pin me? Because my share screen is.
I see lots of team members from Iris. But do you want to
Iris
show
Banin.
us?
My name is Banin. My name is Banin. Can you pin me? Iris Banin, and I'm sharing my screen for the presentation.
Can you, show your hands up? I can.
Oh, right hand. Okay. Here I am.
So you want to? Okay, I see you.
Yes, you see me?
Please go on.
Okay. We are from Institute Teknologi 10 November, or you can say 10 November Institute of Technology. IRIS, abbreviation of ITS Robot with Intelligent System, is a robotic team that focus on autonomous soccer robot. We would like to talk about a breakthrough for RoboCup's future challenge, which is playing on outside field. And we want to talk about RoboCup's objective in 2050, which is winning against human soccer world champion. We believe that in such condition, it is not recommended to use OmniWheel as odometry. Why? Because grass could tangle up in the OmniWheel and it could hamper the bearing, so it will not rotate smoothly. So we came up with an idea of using CNN combined with line mark and gyro compass for self-localization. And I will explain the detail. So we combine OmniVision camera and gyro compass as a self-localization. And inside the self-localization, we use image pre-processing and line mark calculation processed into visual modeling generator and then applied to CNN. The CNN will return a result of the coordinates of the robot as the robot's navigation. A normal CNN would be omnivision and then self-localization, but we also use gyro compass. Why? Because if you see in the left one, when the robot's in this particular position and the right one in this particular position, the Omni camera will return the same exact image. So how can the robot knows which half of the field he is located? That's where the gyro compass comes in. So when the robot's facing north, he is in this part of the field. When he is facing south, he is in this part of the field. For the image preprocessing, the purpose is to obtain the region of interest of a 360 image. The aims is to get rid parts of the image that doesn't have any important value for the CNN. For the example, the outside field, there are a lot of information like the stuff outside the field, and then we use thresholding and cuts out the unnecessary part. For the line mark calculation, it is a process used to calculate the starting point and the end point. For the visual modeling generator, it's received two inputs. The first input is the pre-processed image, this one, and then we add lines, red lines, to determine the robot's angle. We experiment a little bit with the robots, with the line width and the line length, and we will talk about later. This is the convolutional architecture. We ended up with this particular architecture based on several trials and errors that had been performed before. And in the end, there are two connected layers, which consist of 156 nodes and 108 nodes for class. For the dataset retrieval, we use a global camera. We use a wide lens camera, so it is able to capture the entire soccer field. It is located exactly in the middle of the field, 4 meters above the ground. And we use 9 times 12 meters for the soccer field because it is the standard field for national competition in Indonesia. And then for the dataset retrieval path, we run the robot to walk from side to side, from right to left, move forward, left to right, move forward for 50 centimeter and so on. We use a 50 by 50 centimeters red board and place it above the robot. So from the global camera, it can show the position of the robot. Okay, this is the video for the positioning. As you can see, the red one is the global position, the global camera, and the blue one is the odometry. As you can see, after traveling some meters, the odometry is already drifting, right? So we will use the global camera as the foundation of the position. What's perspective after the pre-processed image? As you can see, so only the field is shown and nothing else to obtain only the necessary value. For the next one is the classification of the field. So it can help the CNN to determine the robot's position. We use an 8 by 108 for classification. So this is the statistic for our experiment. We use a lot of variety from line marks with different length and different width. We also use experiment a little bit with no line mark, and the result is as expected. The accuracy is actually half. Why? Because as I said before, if we don't use any line mark, we cannot determine which half of the field robot is located. And our best accuracy is high 60%, like 68%. We can improve this using more data set. Like before, when we use the forward movement, we use 50 centimeters, we can use the shorter forward movement like 20 centimeters or 10 centimeters. And for there is a video for comparison. I will play it and fast forward it a little bit. So the green one is the CNN prediction. The red one is the global camera position, and the blue one is the odometry. I will fast forward it. As you can see, after traveling so far, the odometry is already drifting about 50 centimeters or so. So in this video alone, it stated that using normal field, I mean indoor field, the odometry is already drifting. So if we use outside field like grass and etc., it will damage the accuracy of the odometry, and the accuracy can be more. It can be worse than this. It can drift more. So for summary, we conclude that using OmniWheel as odometry is not recommended for playing on outside field. Why? Because the accuracy can be reduced because outside field has pebbles, rocks, unflat ground, and etc. And the grass could tangled up in the OmniWheel. So we will only use vision combined with gyro compass. Why we use gyro compass? Because it is used to determine which half of the field the robot is located, and because if we don't use gyro compass, the accuracy is actually half of it. So, and with the help of line marks, we can improve the accuracy with different length and different width. We can experiment a little bit to change the accuracy. The data set can be improved also with reducing the forward movement distance when the dataset retrieval path. So from right to left, then forward movement, usually use 50 centimeters. We can reduce it to 10 centimeters to achieve more data. And we believe that using the combination of CNN, gyro compass is better for playing on outside field rather than using only OmniWheel and odometry. And hopefully, this method can fulfill RoboCup's objective for 2050, which is winning against the World Cup champion, human soccer, and also one of RoboCup's future challenge, which is playing on outside field. That's all from Iris. That's all from me. Thank you for your attention.
Thank you, Iris. Any questions?
Yeah.
I have a question. Yeah, I'm teacher, and I would like to. I have heard that how do you play your robot outside? Yeah.
You can play it on outside grass like real field, but we use the national standard, which is 9/12, so it can only play an outside field. That's the exact same field, which is 9/12 meters.
Okay. Thank you.
Okay.
Maybe one question. Do you hear me?
Yeah, I can hear you.
Okay, yeah. Did you experience any issues with compass? Because it's very stable in an outdoor environment, but if there are some electrical connections or cables for light, for sound, for anything, such as RoboCup, for example, it can change a lot the magnetic field locally and raise issues. I think other teams had some problems with that in the past.
Yes, for the issues, one of the main issues is the drifting of the gyro, because it actually very it's important because why we use gyro to determine which half of the field the robot is located. So if the gyro compass is drifting, the accuracy is also becomes lower. So that's that's our main issue so far.
Thank you.
Okay, thank you.
I have a question in the sequence of Valentine's question. Are you using a gyroscope or a magnetic compass? I got a little bit confused because you talked about the compass and then answering the question, you talked about the gyro.
Yeah.
So it's a solid state gyro that they're using, or is a magnetic Earth compass?
Okay, sorry for the confusion. We use gyroscope. Sorry. We use gyroscope.
So you are using a gyroscope. So it's
Yes.
completely different from my point of view. And I was understanding from the presentation that we're talking about the magnetic Earth compass, which has the kind of problems that Valentine has talked about.
Yes.
Are you also fusing in data for the
Hey, next team is Robot Club Torun.
kilometers or
You are already prepared? Please
No,
try
for
to
the
go to the competition room.
camera and the omnivision. That's all.
okay? Thank you.
Okay.
Any more questions? Thank you, Iris. Next should be the RC Robocop Club from Tulun. And team member from Iris, could you please leave the competition room? Thank you. Team member from Iris, could you please leave the competition room now? Thank you.
Okay, thank you.
Team Robot Club Tulun, are you ready?
Yes, we are.
Okay, thank you. We still have several minutes. Team Robot Club to learn. I will stop share my screen and then it's up to you.
Okay, I will share it. Is it okay?
Yes. You can start if you are ready. It's your time.
Yeah, okay. Thank you very much. Thank you very much for attending this technical challenge. I'm sorry. I have to move there. Okay. Our talk is about playing with humans. As you can see on this picture, it's very far from the former one, which is RoboCup. However, it's what we want to do in the near future, playing with humans at RoboCup. Maybe not on this kind of field, but at least to play with humans with in real condition, unlike Iris said before, playing outdoor also. So in this talk, we will focus on what is really necessary to do so, and focusing on 2 points. Playing with humans raises a major challenge. First one is playing without wireless communications, except for the referee, because when you are playing with human player, they are not able to communicate wirelessly. Second thing is to improve drastically embedded perception, because there is no more shared perception because there is no wireless. This requires robot, humans, landmarks to be identified and localized, and also trying to maintain or reduce hardware costs in order to allow new teams to enter the competition. And third thing is to improve robot skills to be competitive with humans. In this talk, we will focus on point 1 and point 3. And tomorrow, we will focus on point 2 on the scientific challenge. So first one is playing without wireless communication. Standard communication on robots are usually this one. There is a local world map, local world state generated in each robot, shared wirelessly to the base station. The base station make a merge of the different local world map and send it to each robot. This is interesting because there is a perception sharing with multiple point of view, and also map merge on base station, reducing embedded computations, but it's very far from human behavior. We never have seen a soccer game where players have been telling, I'm at 80 meters X and 70 meter Y. That it's not like that it works. So what can we do to avoid this? First is to remove base station. It's a step toward communication removal. Local communication, local world map from each robot can be sent to all robots. Is still sent to all robots, but global world map merger within the base station for most teams at this time can be introduced in each robot. This reduces communication because there is still perception sharing, but there are less communication, reducing latency because global world map is not forwarded to robots. But it's still very far from human behavior. However, it's operational in our robot at this time. Playing with humans, what is really necessary? We have to know teammates, opponents, to distinguish between them, to see the goal position and the approximate location of each player and each landmarks on the game. This raises one question. Is it really necessary to have communication for that? I think the reply is no. Except for referee actions, of course, at this time. Maybe later it will be possible to do something. So we propose a major change in our robots for 2021, which is removing digital communication for being closer to humans in the behavior. There is only local warm-up generated locally and used for robot role attribution, strategy managing, and everything else. There is nothing as a base station. There is no communication outside the robot, except for the red box. Of course, this requires something, improved perception. So what is interesting in this approach, it's an important key of playing with humans because it's close, very close to human behavior, because robots don't advertise the location and perception. And also robots and humans are equivalent algorithmically. Of course, the major change is that we need a more reliable perception on strategy algorithm, considering that every teammate doesn't have the same information. It's more difficult to assign roles, but it's also a fantastic field of research for our league. Second point is is improving perception. Tomorrow we will show an extensive point on that, featuring camera, LiDAR, IMU, and globalization of all that with SLAM Kalman filters. But I will present it tomorrow. No time there. Third point is to improve robot skills. This is our improvement for this year. We have redesigned fully our robots. They are now ready. And we have also redesigned fully our coil gun and the control electronics for the coil gun. Here is the control electronics with focus on safety, especially for dissipating energy when a coil gun is closed, is shut down. On improved power, as you can see, it's up to 60 kilometers per hour with a 2 coils coil gun with the same size as existing coil guns such as Tech United or Once. It has been built using simulation. I will see it. It has been simulated using finite elements and optimized with MATLAB, and the result is that the best number of coils is 2 coils. The interpulse delay between both coils is 7 milliseconds, and the initial trigger position must be outside from 9 centimeters from the inside of the coil. Here are some schematic and simulation. Whereas you can see, we have tried more than 2 coils. We have tried 1, 2, 3, 4 coils to see what is the best possible combination for improving a shooting scale. Theoretical and experimental results are this one. Ball speed. Theoretically, we can go up to 60 kilometers per hour. We have measured more than 50 kilometers. This gives a max shooting distance at first rebound of 28 meters. And as shown in the video, we are close to 25 meters. It's reproducible for other team because it's part of published papers, and design is shared on GitHub. And also, we can note that it's better than existing solution, especially for ratio energy volume. As you can see on the table here, it's taken from the paper. We have made a comparison between our optimized coil gun, a former one we have already optimized, a robot arm, a rotating inertial launcher, and a soccer player leg. And energy compared to volume is 10 times better than a human leg. 5 times better than a rotating launcher. These results are interesting and show that it's possible to play with humans in the near future on the robot scales. This has been, I said, published as a research paper on applied physics, on actuators, on also on Robotics Symposium 2019. And for further work on this point, we want to make some model. We're taking into account ball deformation and energy transfer model. In conclusion, 3 keys for playing with humans. First one is playing without maybe not digital, but wireless communication. Second one is improving embedded perception, and I will show you that tomorrow. And the third point is improving robot skill. There are much to do, as Iris said before. We have introduced a new coil gun, but of course, a new mode of propulsions can be also introduced. I'd just like to thank you for listening, and you are very welcome for collaborative research on all this field. And our code will be fully shared on GitHub after the competition at this following address. Thank you for your attention.
Thank you. Any questions?
I have one, very simple one. Have you modeled the response of the ball from the kicker, taking in consideration the internal pressure of the ball?
No, it's what we want to do. It's not yet done, but pressure is difficult to model, and we have to make some modelation using advanced software such as ADAMS, for example. But it has not been modeled. It's modeled from a functional point of view. But,
okay,
however, results are very close to predictions. I think
okay.
less than 10%. It was already the case with the former models.
So for the real measurements, what pressure do you use in the ball?
We have used the competition pressure.
The competition, but the competition is already within 2 values, right? So
I'm not exactly sure, but it's like a real soccer ball.
Right. Okay. Because my perception is that, of course, the pressure of the ball has a huge impact in the result you can obtain while shooting a ball. Okay, thanks a lot.
Yeah, I think there are some more things to improve, such as the plunger, the contact between the ball and the plunger. This can be improved also a lot.
Okay, thank you so much.
You're welcome.
I have a question. What material you use for the plunger and why you use separate coil for coil gun? Thank you.
Thanks for this question. The plunger is in iron, and there is an extension in aluminium because aluminium is a non-magnetic material. And the plunger slides into the rod is in iron, and it slides into a tube which is in inox, which is amagnetic also. Why we use 2 coils is very simple. When you use 1 coil, you have the plunger. I don't see if you will see something. You have the plunger outside, and you put all energy from outside. But the second part, if you have a big coil, let's say that is the second part, that is the first part. When the plunger is here, contribution of the second part of the coil is null, because there is only contribution when the rod is very close to the coil. If the rod is far from the coil, this part of the coil doesn't contribute. So it's better to first make a contribution of the first coil, and when the plunger enters the first coil, the second coil is triggered. And there is a double acceleration reaching, I don't want to say, yeah, it reached 130 G. Yes, 130G, and we spend 130 amperes by coil under 450 volts, I think. Is it clear? To complete just a little, we make some tries with 3 and 4 coils. The tries are fully described in the paper, but it's a little bit better, but synchronization has to be very, very precise. If we are using, for example, 4 coils, and it's not necessary to go to 4 coils, so you only win something like 4% between 2 and 4 coils, comparing with 50% between 1 and 2 coils.
I have any question? What the series of aluminum and iron for use?
Just now I can tell you, but I can tell you, I can give you I can give you the reference after the technical challenge if you want. Of course, you're welcome. But we bought this part from.
Next is new boat. If you are ready, please try to move to the competition.
Very standard aluminum.
Okay, thank you.
You're welcome.
Thank you. Thanks, teams. Robot Club Toulon. Thank you. Next, we will have Newbert here. Team Newbert. Team Newbert, because you have 5 minutes for demonstration. So if you want to show the demonstration via the camera, please pay attention to turn on the camera. Okay. Now, Team Newbert, I will stop share my screen and it's your time. Team Newbert, are you ready?
Can you hear me?
Yes, we can. It's your time. You can start your presentation.
Can you see the PPT?
Yes, please.
Okay. Hello, everyone. I'm Xu from Newbot. The title of my presentation is Efficient Trajectory Generation and Tracking Method for Ball Interception. This work is inspired by a ball catching video of the UAV, which is similar to the ball catching action in MSL. Both of them aim at catching a moving ball, a football for our soccer robot, while a tennis for the UAV. Our soccer robots use the active ball holding subsystem, while the UAV applies an attached ball pocket. The amazing performance of the UAV motivates us to improve our ball interception skill. Previously, we decomposed the ball catching action into 2 steps. Rotate the robot and then move towards the ball. In this work, we propose a new method to solve the geometric and temporal planning problem. The framework of our method consists of 3 parts: an omnivision sensing module to detect the ball and predict its movement, a trajectory generation module to generate a feasible interception trajectory, and a trajectory tracking module to control the robot. Later, we mainly introduce the trajectory generation module and the trajectory tracking module in detail. The trajectory generation module can be divided into 3 steps. Firstly, multiple interception points are generated based on both predicted trajectory. Interception points are made up of interception positions and interception velocities. On both predicted trajectory, we sample both positions every 0.1 second. All interception points are sampled around these predicted positions of the ball, which are shown as small black discs in the figure. For each interception position, its interception velocity is the sum of the ball's velocity and a relative velocity towards the corresponding predicted position. Then, a successful ball interception can be defined as following. The robot arrives at an interception point when the ball arrives at the corresponding predicted position. Secondly, we use the concept of motion primitive in trajectory generation. Each motion primitive starts at the robot's current state and ends at the interception point. For each interception point, the motion primitive generation problem can be formulated as an optimal boundary value problem. As mentioned above, the start state of the system is the robot's current state, whose initial position and velocity are PO and VO, respectively. The end state is determined by the interception point, including the interception position PF and the interception velocity VF. We choose acceleration as our system input. Correspondingly, we select the square of acceleration as our optimization target. The optimal control input, AT, is a polynomial. Alpha t plus beta. Alpha and beta can be directly computed with start state, the end state, and the arrival state. Then the motion primitive can be described as a position polynomial. Due to the analytic polynomials of motion primitive, the computation time is less than 10 microseconds per motion primitive. Thirdly, we will filter out unfeasible trajectories. Each primitive has to satisfy the kinematic constraints. In this work, we mainly consider the input constraints, such as the velocity and acceleration. Besides, each primitive also has to satisfy the safety constraints, including ball avoidance inside the field and obstacle avoidance, just like collision detection module and the sample-based path planning algorithms. We confirm those constraints by sampling states on the motion primitive. Once a sampled state violates these safety constraints, the motion primitive will be marked as unfeasible. Meanwhile, each primitive also has to satisfy the arrival time constraint, which means that the arrival time of the ball must be equal to that of the robot. Finally, we will find the optimal motion primitive from all feasible motion primitives, which is our optimal ball interception trajectory. We give priority to the feasible motion primitives with minimum arrival time. Since the surrounded interception points of a predicted position share the same arrival time, we will compare their optimization targets to distinguish them. In a word, the motion primitive with the minimum arrival time and the minimum cost will be the optimal ball interception trajectory. The third part is our trajectory tracking module, which is built based on the linear model predictive control algorithm. Here, the reference trajectory is described by reference positions, P reference, and the reference velocities, V reference. Same with the OBVP in motion primitive generation. The system input is acceleration. The prediction model and optimization targets are shown in the slide. Although it's very simple and easy, it's indeed a valuable and efficient control algorithm. Here is our experiment. The proposed method is verified in both our simulation platform and the real robot. The simulation platform, CMatch, is an open simulation platform based on ROSE and Gazebo. Previous works of our team have proved its reliability. The robot will track the midfield circle and plot in the right. Next, let's see the trajectory generation video. First, we show the static ball interception. I move the ball. The robot can quickly change the trajectory to catch the ball. The left window shows the field, and the right window shows our motion primitives. The red line represents the execution trajectory. Then, catch a running ball. Obviously, the displayed trajectories point to the predicted ball. The robot can catch the ball in any direction. Finally, avoid obstacle. When the robot is close to other robots, it will replan and actively avoid them. Next is our demonstration.
Wait a moment, I mean to switch the screen. Is this Which is this point of view is right or not? I think you have opened several cameras. Which one you want to show to us? Team Newbot, can you hear me?
Yes, yes.
Newbot, could you please hands up to show which camera you want to show? I see two.
Yeah, and I told them, yeah.
You have two camera. Which one you want to show?
Yeah, and I know.
So you just open the camera you want to show, not all. You have two camera. Understand? Newbot C Charlie, they all have opened the camera. I don't know which one you want to show to us. Okay, thank you. You can start if you are ready. You can explain what's going on here.
Let's see the examples dynamic intersection species. And intersectable.
Could you please repeat? I can't hear clearly.
Two players pass each other to test the reliability and the real-time capability. Player 1抓起决斗 ，Player 2差不多了。其他看决斗，开始多生气。
Excuse me, it's not clear enough of your sound. Could you please double check which mic you are using now? It's totally different with what you just used.
Two players pass each other to test the replay reliability and the real-time capability.
Is that all?
Yes, that's all.
Okay.
Can you see the PPT?
Yes.
That's all. Now it's question and answer section.
Any questions, please?
I have a question. Yes. Usually when we use physics formula, like you said, there are a lot of error factors. Do you experience? I'm sorry. Do you experience any issues while implementing this physics formula?
Oh, sorry. I can hear you clearly. Yeah. So maybe can you pardon your problem? Yeah. 你听到我说话了吗？他说话呢？
Maybe next question, please.
Well, I have a question about the first of all, I want to say thanks for your work and presentation. But my question is about the slide 5 and 6. On the slide 5, you said you update the trajectory every 0.1 second, if I'm not mistaken. And on slide 6, you mentioned that you update the trajectory less than 10 microsecond. But the question is that even on the demonstration and also mostly in the first slide when you show the video, there was many accidents, between robots, and especially between your teammates, robots. I want to know that, my question is that accidents are basically because of the multi-agent trajectory or because of the delay of image processing, which one of them? Or it's because the rate of the updating of the trajectory, because when you consider trajectories, probably should do it for multi-agent, and it would be better if you had the two robots in demonstration to just show us that there is no accident between teammates and the trajectory is updated very fast. So my question is about what is the problem of the accidents in the first video?
I think that I thought our robot a lot in all green. Our robot is not in a good state. So our algorithm show performance better in the simulation. While when it comes to the real robot, the motor and the sensor, one of them decrease the performance of our algorithm. In the future, our team will improve the sensor module. Actually, it's prediction and the protection and the prediction is not as idea as we expected.
I get it, but just my question was that's accidents because of the delay of the, image processing, or because of the multi-agent trajectory, the problem. I think the multi-agent trajectory is regardless of the accuracy of the sensors. If they are very accurate, they get accident again. It's not the idea.
You mean the accident?
Yeah, in the
Actually,
first video on the first slide.
the first video. Actually, in the video, yeah, in the demo demonstration, we many want to show our robot chatbot. So our team member, yeah, the kickboard or the headboard, yeah, accidentally. We just want to show the robot. The robot can check the ball and test the ball.
Hi. Next is Tech United. If you are already prepared, please try to go to the
communication
Thank
between
you.
our team member. Yeah, because some team member is on the field and some team member is in the room. Yeah, there are some problem in our communication. Yeah, can you have I answered your problem?
Actually not. I mean, well, but that's fine.
Okay, thank you, Team Newbert, and you can stop share the screen. I will share my screen. Thank you. Next team should be Tech United from the Netherlands. Hmm? Team Tech United, can you hear me?
Yes, we are here and we're ready.
Okay, I will stop share my screen and it's up to you. Team Newbert, team member from Newbert, please leave the competition room. Thank you.
Okay. Hi, everyone. Can you see my screen right now?
I see the logo of your team, but not very clear. Is a video?
Okay.
Okay, thank you.
Well, hi, my name is Ense Kokkelmans. I'm the current team leader of Tech United, and today I'm going to present you what we did for a technical challenge using a video. At the end of the video, you can ask me questions, and under the video, there's an explanation of what we did and how we did it for you to follow. Enjoy the video. There's a famous saying that in soccer, the worst blindness is only looking at the ball. You have to build up your situational awareness so that you aren't surprised by any last-minute cross or a great pass. Body language plays a huge role in soccer, and for this challenge, we taught our robots how to interpret it. Body language can be used in two completely different ways. You can use the orientation of a person's hips and knees to determine where they are going to move next. Some coaches view this as football instincts. You can also use body language to communicate between teammates on the pitch. On the front of the robot, we've placed a Kinect camera. This camera was previously mostly used for recognizing the ball. In order to detect open post 2, the Kinect camera sends depth and color pictures to an embedded computer which is added on board. The embedded computer runs OpenPose on the color image, and this produces 2D key points for all joints of all people in the image. We use these 2D key points and their corresponding depth to calculate their 3D position on the field. These points are sent to the robot's main computer, which performs the detection of a raised hand or spread legs. Then, the corresponding action is triggered by our skills, tactics, and plays architecture. One straightforward example of the advantage of using open post detection over our previous detection method is getting a more precise image of where the opponent's ligaments are. Using our previous detection method, Johan is detected as a single cylinder. In this case, we can't take advantage of the fact that his legs are wide open. Using open pose, however, we can detect his legs individually and embarrass him a little with a goal right through his legs. Open post detections can also be used as a form of communication between a robot and its human teammates. In this case, we detect which player raises their hand and interpret it as a request to receive the ball. The robot can detect whether its teammate is raising their left or their right hand and shoots the ball to the corresponding foot. This can be used as a new form of communication between humans and robots during mixed team gameplay. This real-time implementation of OpenPose can be used in many different ways in the future. The robots could, for example, interpret the hand signals of the referee instead of receiving commands through the ref box. We could better predict human actions, which can both increase human safety and improve our strategy when playing with humans. We could even use OpenPose to predict in which way the goalkeeper is going to move when taking penalties and shoot the ball in the opposite corner. Our vision is that OpenPose detections are a vital part of our roadmap to winning a match against the human world champions by the year 2050. Thank you all for watching. Are there any questions?
Questions, please. questions, please.
Yeah, one question. Thanks for this very interesting talk. Could you tell us what is the computational power required for embedding this in the robots?
We use an embedded computer, which is the Jetson Savior NX.
Okay. And is it fully used or used at what percentage?
It is fully used, yes.
Fully used. Okay. And can you repeat the Jetson
Jetson Savior with an X and then NX attached at the end.
Okay. Thank you very much.
Other questions?
Well, I have a question. I mean, it's not really a question, it's more a notice. Well, that's first of all, thanks for your presentation and very interesting work. Just to mention that in competition between robots, probably Kinects will have, well, considered as active sensors that make probably noise on the others, but for human playing with human, it should be fine. Just to mention that, well, if new teams wants to add something like this in their robots, they should aware that using active sensors probably will not be possible during a robots match because it will make noise for the others. Yeah.
Okay. Other questions? No more questions?
I do have a last question. Thank you for the great presentation, by the way. I was wondering at what kind of speeds are you performing this detection? So maybe something like 30 frames per second, or?
So there was a configuration problem because we were able to run it at 100 speed with power.
Sorry, I can't hear very clearly. Okay,
should I repeat my?
I'll start over. There was some problem configuring OpenPose because we were able to run it at a higher frame rate on a less computational power full device. But we were able to do this already with only 2 frames per second.
Okay, thank you.
Any other questions? No, then thanks everyone for watching. Yeah. Thank you very much for your questions as well.
If no more questions, thank you. Thank you again. I will share my screen. Next team will be the Hibikino Musashi. We still have more than 10 minutes, so we should wait for them to get everything is ready for the competition.
So Tech United finished the present technical challenge. So next is Hibiki no Musashi. So please go to the competition room. Thank you.
Team Hibikino, if you are ready, you can tell me. I can start the challenge a little earlier also. Thank you. Team Hibikino Masashi, are you ready? Can you hear me? Team Hibikino Masashi. Team Hibikino Masashi, are you ready? No. Moiko, can you hear me? Moiko.
We hear you, but maybe
I see the team member in the chat. They said they can't hear me. Kim Himikino, are you ready? Kim Himikino.
Hi, yes.
Okay. So I will stop share my screen and it's your time.
Thank you.
Okay. Himikino, it's your time.
Thank you.
Himikino, you can start. It's your time. It's already 2 minutes past. Himikino.
Sorry, can you hear my voice?
Yes, we can.
Yes, yes.
Thank you. We have had some problems, so sorry. I want to share this screen. This is a movie. So we would like to talk about our team's activities. So we are Hibiki no Musashi, and we try to cooperate with human and robot. So now this is our robot. So our target is human and robot cooperation. So until now, human try to feed the robot, but from now we have to think about how to make the robot that can feel the human's feeling or some next action. So our suggestion is our RoboCop target is human versus robot team, but our target is human and robot team and human robot team. It's more difficult, but it's really should research in the future, we thought. So cooperative is very important. So this is image our target. So play with human and robot. So today we wanna show you the demonstration of the play with human robot. So human is we use our team member, and robot we use our Hibiki no Musashi's robot. So from now, start the movie. So robot try to pass to the human. The human try to pass to the robot. Also, we try to the human play with human robot, but the human is kids like this. And shoot. So now is we try to use the color. Sorry, we use the YUV space, but it's a little bit difficult because sometimes the color is not stable. So, but now we success about the distance of the object, like a ball and the obstacles. Also, we can know how large the field. But in addition, we are also working on the object detection using the Europe V4. We make our own the human and robot data. And this is the other things. Also, we try to improve the finger. still now, until now, we use the plastic finger, but we didn't know how torque we need. So we did experiment, and 40 Newton is best we found. Also, we try to make the good environment. So until now, we prepare the field each time, but it's very difficult for us. So we paint it on the floor, and now also we try to use the wireless charging. So final goal is using like these technologies, human and robot and environment cooperation. So this goal, we need the communication system. So we try to environment development like that system. Thank you. That's all.
Thank you. Any questions, please? Any questions, please?
Yes, maybe one.
Thank you.
Yeah, could you explain again the system you are using for setting up a field in a very short time? It's very interesting.
The field is...
Yeah, it's at the end.
Here?
Yes.
Yes. Every time we prepared the field, and this is very large, and it takes 1 hour for preparing. So we got the concrete, the factory's field, and we painted on the floor directly.
Okay.
Yes. But maybe we have to improve the foil, the material, because sometimes it's get the slip. Yes.
Any more questions, please? Any more questions?
Maybe a second one. Why are the fingers used for?
You mean why? What's for of this finger?
Oh no, I think the 2 black rods. Maybe just after, maybe, or just before, I don't know.
Oh, this is...
Yes, this.
Yes, because we want to make the stable velocity, so we made the slope for the experiment, and then we changed the distance, and we made the stable velocity to stable velocity. For that, we use these 2 stick, the black stick.
Okay, if no more questions, we should say thank you to Hibikino and thank all teams for today's challenge. Could you please stop share? I will share my screen. Thank you.
Thank you very much.
So please, the team member of Hibikino, could you please leave the competition room? Thank you. So I will say something to the team leaders. So from now, we have, I suggest we use half an hour to give the final score to every team. So for team leader, you can use the Google Driver. You can directly give the score in the Google Driver score tape. For the team leaders, you cannot use the Google Score. I have already sent the table to you, and you can finish the score and send the table back to me by email. Thank you. We have 30 minutes for score. Thank you. Up to now, we have finished the technical challenge for the Middle-sized League 2021, and we will use maybe one hour more or more to calculate the final score, and we will publish the score at the page of Middle-sized League 2021 for the audience, and for all others want to know the result, please scan the QR code at the right corner of the screen. You can get the website, the page of the website, and you can follow us to get the new and get the result and the schedule for the next day. So thank you. First, I will stop the live broadcast, and team leaders, please just wait 1 minute. I will stop the live broadcast first. Thank you.